Good afternoon to everyone. On behalf of Electronics and Communication Department of IMT College of Engineering, myself Pankaj Jha welcomes you all in fourth session of FDP on recent trends and innovation in electronics engineering. Professor Dr. Rajiv Sharma is our eminent speaker for this session. I would like to say something about Dr. Rajiv. Sir has completed his MTech from MNIT Jaipur in 2004 and he awarded PhD degree from Guru Gobind Singh Indraprasth University in 2013. Sir is having more than 22 years of working experience in teaching and presently Sir is working as professor and head in ECE department at Northern India Engineering College, Shastri Park, New Delhi. Previously, Sir worked as a director in Geeta Engineering College, Panipat. Sir worked as a professor and head in SGT Institute of Engineering and Technology. Apart from this, Sir worked as a coordinator AICT sponsored national level seminar on VLSI design. He was member of syllabus committee and member of board of study in University Institute of Engineering and Technology. Apart from this, Sir worked as a different aspect of as an academician. Sir published nearly 40 papers in national conference and published 8 papers in international conference. He also published 23 papers in international journals. So in short, a very renowned academician is among with us. Thank you very much, sir, for being with us. Now, I would like to invite our FDP convener, Professor Dr. Seema Nayak, to welcome, sir.
Thank you, sir. Very good afternoon to all, and I heartily welcome to our today's speaker for the session 4 of this FDP, Dr. Rajiv Sharma, Professor and Head EC, ADG ITM, New Delhi. Also, hearty welcome to all the participants. Today's his topic is VLSI design, and also here I want to share that I have completed my BTech in 1994 from Maharashtra, and Dr. Rajiv was my senior, my elder brother. And I thank you this pandemic situation that this situation has clubbed all of us on this same platform, and I am very happy to meet him after a so long time. And I also wish to all to stay safe at home. Now I would like to invite our today's speaker, Dr. Raju Sharma, to share his knowledge with us.
Dr. Seema Nayak, for your nice words. Good afternoon, everyone. Today I'll continue with the topic, recent trends in electronics. Primarily, my focus will be on VLSI technology evolution. I'll keep my presentation in 5 sections. In section 1, I'll talk about the evolution, the 4 generations of evolution, starting from vacuum tubes to solid state devices. Primarily, I'll be discussing transistors. That was possible because of semiconductors, again a revolution in electronics field. From there, then I'll talk about evolution of ICs. Section 2 will comprise of the evolution of a very important IC, that is your microprocessors, which we also know is defined as a central processing unit on a single chip of a computer. Here I'll talk about the evolution of microprocessors, starting from the first Intel 4-bit processor to the today's 64-bit processors. Section 3, I'll talk about the IC technology evolution, wherein we know that it all started with small scale integration, then we went to medium scale integration, large scale integration, very large scale integration, and ultra large scale integration. Here I'll talk about VLSI design flow. I'll illustrate with an example. Then in this context, being a person with an electronics background, I'll talk about the CAD tools that we use and why we needed CAD tools and what are the various CAD tools that we can use in VLSI. Here again, I'll give an example of a open source tool that is called a layout editor that is used for design of layout of transistors with a suitable example. Section 4 will comprise of implications of these developments that I've discussed in the primary 3 sections. And here I'll be focusing the implications in the field of consumer electronics, medical electronics, and wireless communication. And then I'll conclude my presentation today with the biggest trends in 2020, that is present year, which have led to the transformation in the telecommunication industry or telecommunication field. So, okay, let us start my presentation with section 1. So here I'll talk about the 4 generations evolution. You can see on the screen, it all started in 5000 BC. We had a mechanical age. We had a mechanical calculator with gears and wheels. Okay, then the first generation vacuum tubes, it was from mechanical, we were transforming to electrical age. In 1889, we had the first electronic numerical integrator and calculator comprised, it was a general purpose programmable electronic computer comprising of 17,000 vacuum tubes, 500 miles of wire, 6,000 switches, and the lifespan of these vacuum tubes were 3,000 hours. So maintenance was a big challenge. So as the technology advanced in electronics industry, so we had a number of developments. Let's see them in a systematic order. 1875, we saw the first phototube. 1878, we saw the first prototype of a cathode ray tube. 1895, a prototype for a X-ray tube. 1897, we saw the first CRT oscilloscope, that is a cathode ray oscilloscope. 1904, we saw the first Fleming vacuum tube diode given by after the name of the scientist, John Ambrose Fleming. So this was a big invention, vacuum tube diode. So triode, as the name indicates, comprises of 3 electrodes, a node, cathode, and one controlling another plate that is controlling the transmission of charge carriers, that is electrons from cathode to a node. So again, in this particular context, so it was in 1906, Lee D. Forrest invented the first Audion, later called as triode, which was an improvement over the Fleming wall diode that was a vacuum diode. 1913, William D. Coolidge invented the Coolidge tube, that was the first practical X-ray tube. In 1920s, we started with the commercial electron manufacturing. And with this first generation of devices, vacuum tubes, the limitations were the size was very large, huge amount of power dissipation was there. The time of operation was definitely fixed, as we've seen in the earlier slide. And the response was not good, and they were very expensive. So next generation of devices, that is the solid state devices, where I'll be discussing about transistors. It was possible because of semiconductors. We know that semiconductors are the devices which have conductivity between conductors and insulators. Here in semiconductors, the valence band is complete, conduction band is almost empty. So depending upon, we are familiar with 2 kinds of semiconductors, germanium and silicon. So there's an energy gap, which after applying some thermal energy, we can overcome, and then the electrons can move from valence band to conduction band and contribute to the conductivity. So there are primarily 2 types of semiconductors, intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductor is primarily in its extremely pure form, is any semiconductor is called Intrinsic semiconductor, it has a very little current conduction capability at room temperature. Extrinsic semiconductor, to this pure semiconductor, if we add some amount of impurity, so we call it a doping, so that will lead to extrinsic semiconductors. There are two types of impurities we can add. We have impurities from fifth column, semiconductors, and it is from third group. They contribute to p-type semiconductors. So as you can see that either we add arsenic or antimony, so these impurities will produce n-type semiconductors. They will call a donor because every impurity atom is contributing or donating one free electron. Similarly, trivalent impurities, we have gallium, indium. So these impurities which produce p-type semiconductors are called acceptor impurities because here the holes are created with every impurity atom added. Now in solid state devices, I'll skip in semiconductors, I'll skip the p-n junction diodes because I'll straight on come to transistors. So the field of electronics shifted from vacuum tubes to solid state devices because of the invention of the transistors. And the first transistor was given by Bardeen, Breton, and Shockley in 1956. So these transistors, they contributed or they led to the evolution of generations from first generation to second generation. Initially we had BJTs, so mainframe computers were there, circuits were made on frames, panels. So again, in this, the revolution in solid state electronics, we had BJTs, then we had first silicon transistors that was produced by Texas Instruments in 1954. And then again, a very big revolution in this electronics industry came due to the invention of first MOS transistors that was built by Kang and Atala in 1960. The advantages of these transistors was the size was small compared to the earlier generation vacuum tubes, weight was less. So we could, we'll see that primarily in ICs, that is the concept of miniaturizations. So that was these transistors, small size and minimum weight were allowing the development of these miniaturized electronic devices. Cost was less, operating voltages were less. So because of this, the battery powered applications, they were suitable for. As it was required for heating in your vacuum tubes, cathode heaters was required, so no more warm-up was required here. Low power dissipation is again, and a better efficiency advantage of these solid state devices over the vacuum tubes. Life was better, extremely long life. Some transistor devices have been in service for more than 50 years. Now up to 60s, the electronic circuits were very bulky. At that time, electronic circuit consisted of various discrete components. They were comprising of BJTs, resistance capacitors. So these circuits were called discrete circuits. So these circuits consisted of very less components and they occupied a very large space. So need was, there was a need so that we can have more number of components. So the answer was found in 1958. So that is your IC that was invented. So we all know what an IC is. So the integrated circuit is a circuit which comprises of transistors, diode, resistors, and they all are mounted on small piece of semiconductor. So this is how the first IC was developed. So now we moved on from first generation, that is vacuum tubes, to solid state devices, to third generation, that is ICs. Again, the advantage of ICs, reliability was improving. There were less number of connections. The size was smaller, lesser weight and space required, low power requirements. It is greatly able to operate at extremely low values of temperature, low cost. Circuit layout is greatly simplified. Disadvantage is that if any component IC goes out of order, the whole IC has to be replaced. Whereas when you're dealing with the discrete circuits, we can simply replace that component. Here, if any IC goes out of order, we have to replace the entire IC. And again, a limitation is it is neither convenient nor economical to fabricate capacitances exceeding 30 picofarad. It is not fabricated to introduce inductors, transformers, and they all are basically not suitable for high power ICs, that is beyond 10 watt. So this is your third generation evolution, that ICs. So 1958, first IC was there. Now this winds up the first phase of, or first section of my presentation, that is the evolution of 4 generations. I started with vacuum tubes, then we talked about solid state devices. There, due to the semiconductors, we had transistors, and then from transistors, we have from discrete components, discrete circuits, we moved on to ICs. And here I have deliberately taken this IC, which is a central processing unit of a microprocessor. So the section 2 of my presentation comprises of this evolution journey of Intel processors. Primarily, I'll be talking from your 4-bit processors to 8-bit, 16-bit, 32-bit, and then 64-bit processors. So if we have to tell what a microprocessor is, so on your screen you can see the simplified block diagram of a computer system comprising of an input device, that is a keyboard, output device, normally it's a display, a central processing unit, which we'll be discussing in detail, that is your CPU on a single chip, as microprocessor. And you can see that this processor does not have a memory, so we have to connect a memory. So see that we have 2 types of memories connected. So as we move from 4-bit processors to 8-bit processors, we'll see that what is the role of main memory and when the secondary memory or backing storage came into existence. So now I'll take this journey of evolution of microprocessors from 4-bit to 8-bit, 16-bit, then to 32-bit, and finally a 64-bit, that is 2-days processor. If you see that when we say that it's a 4-bit processor or a 8-bit processor, 16-bit, so we are talking about word length. So we all are enjoying today's i7 Intel Core 10 generation processors. Recently, I was going through the literature. As on today, even Intel has gone beyond 5 gigahertz in terms of the clock speed. It has even gone beyond that. It has the latest Intel processor, actually series processor, is working at 5.3 gigahertz. So this is 4-bit, 8-bit means that word length of a processor. So we'll see that as the technology advanced, what were the major changes? So 4-bit, 8-bit, 16-bit, they talk about the data bus, how much data you can process in parallel at a time. So again, you see that the earlier diagram, it was simply a CPU comprising of arithmetic. The diagram was comprising of an input unit, output device, a CPU, RAM, and this structure, it is your advanced processors. I'll come back to this slide again. First, let's go through this evolution. As I've told you, the first processors, Intel processor came in 1971. It was a 4-bit processor. On the screen, there are a number of vendors. They are making microprocessors, Motorola, 68 series, Xylo. So I'll be primarily focusing on Intel processors. I'll be discussing Intel processors from 4-bit to the today's current 64-bit processors. 4-bit, Intel had 4004 first processor. It was a 4-bit processor. As you can see on the screen, bit length is your data bus, and process technology. It is the feature size. In ICs, the major component is transistor. As you can see on the rightmost column, the number of transistors and the technology it uses. So the initial 4-bit microprocessors were using PMOS technology. and the feature size was 10 micrometer on that processor. So, and if you talk of the clock speeds of this processor, 4-bit processor, they were ranging from 540 kilohertz to 740 kilohertz. Then came your next series of Intel processors that we call as 8-bit processors. In this we had 8008. Again, it was 8-bit processor. The feature size was 10 micrometer. The transistor count has increased from 2 to 50 for a 4-bit processor to 3500. Again, the technology it was using MOS transistors. In MOS, if you see that the earliest, first of all, we had PMOS transistors, then we had NMOS transistors, and then finally we had CMOS. So the initial devices or the ICs were comprising of PMOS technology, and we all know that NMOS is definitely faster compared to PMOS because the mobility of charge carry electrons are faster compared to your PMOS transistors. 8-bit processors, if we see that this transformation was going from, the clock speed has gone from kilohertz to megahertz. And if you talk of the register size, because how a processor works depends upon a number of things. As I've told you, word length, number of registers, types of registers, size of registers. So the number of registers and type of registers will vary from processor to processor. If you talk of an 8-bit processor, the registers were 8-bit and they were called Intel. If I'm talking about Intel 8085, A, B, C, D, E, HL, they all are 8-bit registers, B, C, and D, E, HL. They can talk about, they can be grouped together to make a 60-bit register. Then we had a stack pointer and a program counter. They are memory pointers. If you talk of a 16-bit processors, then the first processor was your 8086. It came in 1978. Again, I'll only discuss about Intel processors. You see the transistor count, the feature size. The feature size has gone to 3 micrometer. In 16-bit processors, we had a number of processors: 8086, 80186, 286. If you compare 85 with 86, with every generation, you see that every processor, the things were changing. How we were saying that, how we are supporting the performance is improving. 85, if you have to execute instruction, it was simply fetch, decode, execute. Whereas in 86, we had a pipelining. So what is the meaning of pipelining? That in 86, we have an instruction, we have an execution unit, and we have a bus phase enter unit. So when first instruction is being executed, so next instruction can be prefetched. So this is the concept of pipelining. So that will improve the performance of 8086 processor over 85. Another thing that we have to take into account is the address bus. Bit length talks about the data bus. Address bus of 8-bit processors, if I talk about 85 was 16-bit. So the maximum amount of memory, if you see this slide, processor does not have a memory. If the memory you have to interface with this processor, or a 8-bit processor, a 85 processor, we could interface up to 64 kilobyte. That is, address lines are 16, so 2 raised to 16 is 64 kilobyte. 85 and 86, the address bus is 20 bits, so the addressing capability is 1 megabyte. So up to 8086, 80186, the addressing capability was 1 MB. If you talk of a 286 processor, again there was a change. So 80286, but this was a 16-bit processor, but you see the changes here were happening on that it was having address bus that was 24-bit. So the physical address bus, the memory addressing capability, physical memory went to 16 MB. Again with 80286, another thing started, that was the concept of virtual memory. That is the secondary memory we saw on the previous slide. So this started with 286 secondary memory. The reason was, as you can see, that 8-bit processor, the physical size of the memory that you can interface was 64 kilobyte, 16-bit address lines, 86, 20-bit, 1 MB. So what was happening that if you talk of the physical memory, As the address lines increase, definitely the memory addressing capability improves, but that happens at the expense of increase in number of pins. That increases the size of the IC. So another concept of was utilized, that was virtual memory. So virtual memory is a memory that is not actually physically existing on your system. So in virtual memory, you see that we were using the concept of segment selectors, descriptors. So if you talk of 80286, the virtual memory, it went to 1 GB. So first 32-bit processor, Intel processor was 386. In 386, the register, again, the type of registers, the size of registers, it was a first 32-bit processor. So the register nomenclature changed from AX, BX, CX to EAX, EBX, ECX, EDX, stack pointer, ECS, ESP, stack pointer, EIP, instruction pointer. So they all registers, they became 32-bit registers. You can see that feature size again decreased from 1.5 micron to 0.8, because feature size, as we have to accommodate more and more components, the feature size, the size of the transistor, the feature size has to be reduced. So to accommodate more components on the same space. And this reduction in the feature size was enabling to accommodate more and more transistors, as we've seen on our slides. They have increased from 2250 in the first 4-bit transistor to 386. We can see there as many as 80,000 transistors. Again in 386, we had two models, SX and DX model. Or other changes that we saw in 386 introduced a concept of memory management unit, because here we were having two memories, real memory and virtual memory. So it required a system mechanism to manage both the memories. So it works in two modes, real modes and protected virtual address mode. So when you reset this processor, it was working in real mode, and you can see that it was nothing but a fast 16-bit microprocessor as good as your 8086. And in protected virtual address mode, it was and caching, it was using all the capabilities of this advanced processor. Then came your 80486. As you can see that the feature size was somewhere around 1 micrometer. The transistor count is 1,180,000. So the transistor count was also increasing. Another feature that came on this with 486 was that it had an on-chip math coprocessor. Now, math coprocessor are the series of chips starting from 8087, that was interfaced with 8086, then 8028, 187, 287, 387. 486 के साथ जो था coprocessor was 80487. The good part with this 487 processor was it was on chip with 486. This was a math coprocessor that was enabling your complex mathematical applications that CPU does not have to perform. The math coprocessor was doing it for your processor CPU. So when you have the math coprocessor on the chip as your processor, so the overhead of interconnections and calling these this processor to carry out the task, so that reduced. So these things were leading to improving the performance of a processor. Now next generation was your Pentium processors. So Pentium processors, we have a number of processors. Pentium initial processor was a 32-bit processor. Pentium Pro, we write at 32 or 64-bit processor. If you see with Pentium processors, the advantage was there number of other architectural changes were observed with these Pentium processors, series of processors that include Pentium, Pentium Pro, P2, then Itanium, Itanium 2, Pentium, and the Pentium D. They all are different Pentium processors. So the architectural changes that were experienced or they were given by these processors, I'll be just sharing those. So one was superscalar architecture. So what is the meaning of superscalar architecture? Till Pentium processor, the CPU could execute only one instruction at one per cycle. But with this superscalar architecture introduced in Pentium processor, the CPU could execute more than one instruction per cycle. So it was possible because of more than one execution unit. branch prediction, speculative execution, or out of order execution. Out of order execution means that till Pentium processors, the instructions were executed in a particular sequence, 1, 2, 3, in this order they were executed. So out of order execution also was enabled, was possible in this. And then if you talk of Pentium processors, other main features were streaming your single instructions, multiple data. That is your, up to this Pentium processors, but we could see that if you talk about streaming single instruction, multiple instructions data. So up to before this P4 processors, what we could do that any instruction was only dealing with, was able to process only one data, single data. So with this SSE feature included with the P4 processor, it could deal with multiple datas, and these were very useful in your 3D graphic applications. Another change, or you can see that evolution, was introduction of your hyperthread technology, where Intel terms, in terms of Intel, they talk it as simultaneous multi-threading. Basically, hyperthreading or your multi-threading is a concept where we can, it is primarily used to improve parallelization of computers, or they were enabling or making your multitasking possible, so that you can do more than one task at a time. So basically how this happens is, this SMT or hyperthreading, basically the CPU splits each of its physical core into your virtual cores. Let's say if we talk of a dual core processor, so it has physically 2 cores. So if you talk of, it has this SMT technology, so what it does, it will divide these 2 physical cores into 4 virtual cores. So again, improving your parallelization of computation, multitasking possible. Multimedia register, multimedia extension. Then we have multimedia registers were 80-bit registers. SSE, as I've told you, streaming single instruction multiple data came in SSE 1, 4.2. Then we had this Sandy bridge configuration, where we had 256-bit registers was introduced in 2011. 2016 we have 500-bit your registers. So you see that we only are appreciating the improvement in performance, and internally what was happening, I've tried to share in the allotted time that how these things were possible. So these all were possible primarily because of reduction in the feature size, contributing to improving or increasing your transistor count, improving your moving from improvement in the data bus from 4-bit to 64-bit, address bus, using the concept of virtual memory, features as SMT, multimedia applications, multimedia extension registers, SSC structures. So these all were leading to the processors today that we have today. Again, we also come across nowadays about multi-core processors. So very briefly, I'll just discuss what these multi-core processors are, or they're also called chip-level multiprocessors. It combines 2 or more independent cores into a single package composed of a single IC. So individual core is normally a CPU. So if you talk about dual core processor, it will contain 2 cores. Quad will have 4 core. Multi-core processor implements multiprocessing in a single physical package. So examples, PowerFold was the world's first dual core processor. It was released in 2001. Celeron, dual core processor. CoreDuo, Core2Duo, Core2 Quad, Xeon, Quad, hexa-core processors. So they all were the changes, developments in these processors from 2 core to 4 core to 6 core to 8 core processors. If you talk of in terms of Intel, the Core 2 brand refers to a range of Intel's consumer 60-watt dual cores, MCM quad core CPUs. The Core 2 brand, it was introduced in 2006, initially comprising of a single core, then dual core, quad core, then today we have octa-core processors also. Now, again, along with the other changes that I've discussed, so these graphic applications, the graphic processing unit on a processor, this was also changing, that was supporting or enabling us to play the more graphic intensive games without the need of additional graphic cards. So you can see that the graphic performance from the 4th generation processor increased by 32% in 3D graphics over the comparable 3rd generation systems. So they are available in different forms such as GT1, GT2, GT3, a level of 10, 20, 40 execution units, and at various GPU speeds depending on the CPU. And GT3 was further divided into these series as mentioned on the screen as HD 5000, Iris and Iris Pro versions. So over the generation, you can see that there was, if you compare the earlier processor with the today's processors, so there has been 100 times improvement. If you see in terms of your battery life, video conversion, 3D conversion. So these from 4th generation to 5th generation to next generation. So there has been a remarkable improvement. If we talk of 6th generation Intel, so it was launched in 2015, September 1. So as I've told you, it is built on new Skylake micro architecture. It uses 14 nanometer manufacturing process. You see that we started with a 10 micrometer transistor in 4004 Intel first 4-bit processor. Now we have, even today we have we've reached to 5 nanometer transistors as you see today. If we talk in terms of CPU, we have better CPU part at lower power, longer battery lives, better cameras, 4 HD cameras, better resolution, imaging resolution, video capture, spatial sound, clearer voice inputs, low power, more accurate speed, responsive touch, stylish experiences. So these all are possible with the 6th generation processors. So I'll skip these slides. Already you discussed this. So this entire evolution that we've just seen on our slides in the second part of my presentation is primarily because of this Moore's scientist, Moore's law, that he predicted that with the every 1.5 to 2 years, the number of transistors would double. So this is what it was predicted, and this is how it has been made possible. 4004, and we'll see how it is possible in the next our next section, that is your VLSI design. There we'll see how this evolution has been possible, miniaturization, accommodating more and more transistors, starting with somewhere around 2,500 transistors to up to 1 million transistors today. So again, if we talk of the feature size, we started with micron, and today we have transistors in nanoscale, as small as 5 nanometer transistor being used. So in terms of processor technology, again, this talks about the transistor count. They become smaller, faster, better in terms of performance, low power, and they become cheaper also. So we can sum up this. So in these processors, section 2, we've seen that we have more speed per processor, memory integration was improving. We did not need to work upon the physical memory. We had introduced the concept of virtual memory. So we can have more processors per core, we're having more transistor, we have larger wafers and narrower circuits. So these have been technology trends. Capacity is increasing by 30%, clock frequency is increasing by 20%, cost per function is decreasing, memory is improving day by day, speed is increasing, cost is decreasing. So these all are the factors that are contributing to the present scenario microprocessors that we have. Now I'll talk about the phase 3 or the section 3 of my presentation, that is the integration technology evolution. Whatever we saw in the recent slides, it was all possible because of the evolution in this integration technology, from small scale to medium scale to large scale to very large scale to ultra large scale. It was simply meaning that the count of transistors, why we are emphasizing on transistors, as we have seen that in ICs, the majority of them, the major component is transistors. That's why we're talking about transistors when we're talking about the evolution of technologies from SSI to the ultra large scale integration technology. So here I'll discuss this. I'm starting with the section 3 of my presentation, where I'll be illustrating a VLSI design flow with a suitable example. If you see on the screen on the right, you have a flow chart where we have a VLSI design flow demonstrated in terms of a flow chart comprising of system specification, where we have to specify size, speed, power, and functionality of that VLSI system that we have to design. I'll take example in the coming slides of this system. I'll illustrate the same using example also. Then we have to make a decision on the architecture, whether we have to go for RISC architecture or the CISC architecture, cache size. And then we have to go for the functional design. So we have to design the main functional unit. Functional designer will contribute to the logic design, where we have to express the design in terms of register allocations. The outcome is a RTL level description. So we all are familiar. We've all done at some level hardware description language, VHDL, that is very high speed integrated circuit hardware description language that we mostly study in our institutes, Verilog, which is more used in industries. So this is your VLSI cycle. Next step, circuit design. So circuit is designed that we obtain from logic design is converted into circuits comprising of transistor interconnects. Then we have a physical design. Physical design is a very important component in this design flow, and I'll be taking example. So this is called, we are converting from circuit that we get the netlist into a geometric representation that we call as a layout. Then we proceed to fabrication, and finally we have packaging. So a simplified VLSI design flow will look something like this. On left hand side, we have the front end part comprising of system specifications, functional or architectural design that we've discussed in last slide. Logic design, logic verification. On the right hand side, we have circuit design comprising of the back end part, circuit verification, physical design, and physical verification. Again, the 4 levels of this design representation: behavioral, logical, that is gate level representation, circuit, that is transistor level representation, and a layout representation we are representing in terms of physical devices. Now this VLSI design flow, as you can see through example on your right on your screen, I'll try to illustrate that. I'll try to design an adder from 1 bit binary full adder. So as we've seen on the design flow diagram, we start with the system specifications. So they are mentioned. So in terms of propagation delay, transistor delay times of your sum and carry signals, circuit area, power dissipation. So these are system specifications. So as we all know, you have this behavioral representation of a full adder comprising of AN bit, AN B, 2 binary bits. C is your previous carry, and sum and out are your carry outputs and sum output. So your functional representation is, in terms of expression, sum is A XOR B XOR C, and carry is again expressed in terms of a Boolean equation. You can write it as AB plus AC plus BC. So this is your phase 1 and phase 2, where you have represented, we have given the system specifications, and then we have given the behavioral representation. Now from behavior, once we have the behavioral representation, we can go to your logic or gate level representation. So your full adder, as we have trying to illustrate here, we expressed the sum and carry using your gates, XOR gate, AND gate. So these gates using, we have expressed your logic design. So from logic design, we move on to your circuit or transistor level representation. So here again, depending on the specifications, we have to choose the minimum size transistors. So in order to translate from gate level design into a transistor level circuit description, we see that we are representing using a CMOS realization, and is the series connected NMOS transistor, or is your parallel connected NMOS transistors. Okay, so on your screen you can see the circuit level representation of a full adder. So from circuit level we go to the next step is your physical design and physical verification. So circuit level designer will transfer this netlist and information to the physical design engineer. So the designer should confirm using this DRC's design rule checking tool that none of the physical layout design rules are violated. So if you talk of the design rules, it talks in terms of spacing, overlap. So these are things that we see. So I'll illustrate with some examples in the slides to follow. From that, the next step is to extract this the parasitic capacitance and the resistances from this initial layout, and then a detailed circuit simulation tool, that is SPICE, is used to estimate the dynamic performance and to meet our mentioned specifications. After this, we have a parasitic extraction tool which will read the physical layout, analyze the various mask layers to identify transistors, interconnects, contacts, and then it will be calculating the parasitic capacitance and the parasitic resistance of these structures, and then finally it will prepare a SPICE input file that will describe the circuit. Now here, as I've mentioned, that I'm trying to illustrate the use of this a tool that is called, it's an open source tool, that is a layout editor tool. So here it is used to provide the layout of transistors. I've taken an example of an inverter. Left on your screen is your schematic. In the middle of the screen is your stick diagram, and the right side on your screen is a layout that has been created on this layout editor. It's a open source tool, so it is a backend tool. So if you want to work on this, it's a very good tool, and if you are familiar with this tool, so you have a very good opportunities within the field of VLSI field. Having any knowledge of a front end or a back end tool will definitely improve your chances of performing better in interviews pertaining to VLSI domain. So you can see that this is a CMOS combinational inverter using CMOS combination logic will comprise of the basic. I've taken inverter. The reason is because it's a fundamental element. If you have to compare the performance of any logical family, you have the fundamental component is inverter. That's why I've taken an inverter. So inverter, this inverter comprises of, on top of your screen, you have this PMOS transistor. These are the various MOS layers, source, drain, this is metal, this is your supply, and this is your NMOS transistor. So this is your input, and this is your output, and this is your two supply rails, VDD and ground. Again, some more examples. If we have to work on this tool, you can further proceed with designing of basic structures such as XOR gate, half adder. Then you can work on NAND gate, NOR gates. So if you're familiar with NAND, NOR, inverter, XOR, these configurations, you can build any logic structure, any circuit. Now, the phases, I'll just, because time span, I'll try to just speed up the remaining slides. The phases of creating microelectronics chips, we've seen, we start with design, we go to fabrication, testing, and the final is packaging. So as I mentioned earlier, what was the need of computerized design tools? As we could see that this layout, as I've shown you in earlier slides, the manual layout of complex large-scale design was not practical. So the manually drawing these layouts for billion transistors as of the ICs today, it will take too much of a time, and even it will create a problem. So testing was a problem. So how to reuse designs, how to create human readable designs. So the solution was we can go for electronic design automation, that is EDA tools, that is your computer aided design tools, CAD tools. Since I've been discussing VLSI design flow, so I'll be primarily focusing on the VLSI CAD. So various softwares like Synopsys, Cadence are used by designers to synthesize highly efficient VLSI chips. Hardware discipline, front end where I've told you, you can work upon Verilog or VHDL. I'll just skip this slide. I'll go to the next slide. If you see this, this is the design flow in terms of what we are doing, the various design engineers. So from your VHDL design goes to your next stage to schematic, that is from logic design, circuit design to the layout, design layout will go to your printing, then it will go to making of wafer, then from wafer we are slicing it and we are getting die or ICs, then finally we have a chip. This is the different phases that you undergo when you are making this chip. Again a simplified CAD tool flowchart. We start with the HDL description. We have a schematic description, that is your in terms of your circuit components, then your physical layout, routing again is a very challenging thing. It's a very, all these fields at any point of time, the different designs flow components, each and every component is an independent component. Routing is how you are connecting, providing the interconnects between the various devices on your IC. So the various VLSI CAD tool vendors, Cadence, Synopsys, there are some of them, Mentor Graphics, you all must be familiar, Tanner, EDA, MOS, Implementation Services, MOSes. So these are some of the VLSI tool vendors.
Okay.
The next, section 4, I'll talk about the implication of these developments, primarily in the field of consumer electronics, wireless communication, medical electronics, and in transport electronics, that is automobile industry. Consumer electronics, as on today, we're talking about high definition TVs. So we have switched from analog way of doing the information to your digital high definition ways of extracting the information. So high definition means digital technology today. So here we started with plasma, then we went to LED. As on today, we are even talking about organic LED technology. So OLED displays are even thinner, making them ideal for devices with small, slim designs. We have smart TVs. So smart TVs, we all know the conventional broadcasts are not only things that these smart TVs can receive, they can also access, we can access internet content and services. Photos, music, videos are no longer stored on a shelves in albums or shoeboxes. So we can digitally, you can put them on your PCs, notebooks, and you can hard drives also via home network. You can retrieve them virtually. You can retrieve any digital device. So the communication between this consumer electronic components and household appliances has also opened up a wealth of possibilities in the present scenario and also for the future applications. You know, as on today, we can have our washing machines can be monitored via a smartphone or a tablet, where your owners are on the move. Lighting or blinds in the house can be activated even when you're on holidays. When shopping, users can alter to low food stocks in the fridge. The next phase is wireless communication. We've seen that from GPS to Bluetooth, CDMA, 2G, 3G, 4G, 5G, Wi-Fi, Zigbee. So these all are the recent trends in communication technology. So the mobile phone technology has revolutionized the entire communication domain. Cell phone has become a biggest platform. Up to total wireless subscribers are increasing day by day from billions to trillions. If we talk of the automobile industry, again, these revolutions have aided in providing safety measures, such as safety awareness for vehicles has been increasingly stronger since the 80s. Today, advancement in the sensors and the processor technology, we are having a better possibilities of decreasing traffic casualties. Most car headlights can light the road up to 60 meters ahead. So we have blind spot detections possible. We have in this, what we do is that most blind spot detection system, they are using the radar sensors located behind the rear bumpers that can monitor the sides of the vehicle. So this is again driver alertness. So drivers are not being alert whether they are in fatigue or in distraction. It has been a cause of vehicle crashes. So nowadays we have camera monitors. So these cameras, they are monitoring the driver's head and eye position and the frequency at which the driver is blinking. So again, it is providing a safety measure. Then lane departure warning systems is also possible today, again adding a safety measure to driving. In the field of medical electronics, we have a number of such devices, which is possible because of the development of semiconductors. So these are some of the application in medical electronics. So these are the devices. So I'll wind up my presentation by discussing the 7 biggest technology trends that will transform the telecoms in 2020. Let's just take a look at them one by one. 5G is one of them. It is promising some dramatic changes. It will change the telecom role. The telecoms will not only be technological distribution, but it will also work as service providers. Second is AI. So telecommunication is one of the industries that uses AI in many aspects. Through visual assistant, chat box, artificial intelligence that runs through these tools behind the scenes, telecommunication companies improve the customer service and satisfaction. IoT, because of the telecommunication industry enables internet devices connectivity. It is one of the largest players in the IoT market. So this helps ensure minimal downtime for the network. Since the telecom is so instrumental in providing IoT infrastructure, the industry is uniquely poised to develop and often their own services for IoT. So IoT technology will result in more devices on the network. So there will be more opportunities for security and privacy breaches. And then big data, again, it is undeniable that the telecommunication companies are collecting and generating volumes of data from mobile devices and apps. So the wireless data is expected to continue to increase through 2020s, but it will be the companies that use it to their competitive advantage that will survive. Finally, your robotic process automation can also take away over repetitive rule-based high-frequency processes and can complete the task accurately. When telecommunication deploy RPA for tasks, error rates and cost bills are reduced. Customer services, operational efficiencies are improved, they are boosted. So telecommunication industry has one of the highest adoption rate for this RPA technology. Cloud computing, again, it pays per use service model helps telecom introduce new services, reduce their cost, adjust to the market demand more effectively. And telecom adopts cloud computing and switch important business functions to the cloud. They benefit from the cloud efficiency. Cyber security and resilience. Again, this is a very important aspect. From direct cyber attacks such as distributed denial of service to indirect attacks such as malwares, telecoms need to protect themselves and prepare themselves for the coming 5G and security hurdles. So currently there is a room for improvement to the industry response to a cyber attack. Even false claims of attack can damage to our telecom reputation. We all know that, and as well as create a considerable business impact in terms of time, money to respond. Thank you. With this, I'll conclude. I've come to end of this presentation.
Thank you very much, sir, for giving an entire overview on VLSI and about developments. There are few questions, sir. In fact, in chat box, there are few questions I want to take with your permission.
Okay. Go ahead.
Sir, first question is from a research scholar. He want to know that we are doing a lot in designing, is VLSI designing, but still we are not able to do fabrication at commercial level in our country. What are the main reason behind this?
There are issues actually that they are more related to the current government structure of ours, the structure that we are living today. But as on today, the good news is, if you go through the recent newspapers or the recent news channels, now today the government has started encouraging this even introduction or fabrication of chips in India. They are promoting, they are encouraging. In today's scenario, we cannot say that the things are changing, but definitely if you talk back in 5 years back, that was definitely a challenge. We were not producing the chips here, even wafers here. But as on today, it's technology and the revolution. We see that due to the government support, Atmanirbhar Yojana and things like that, they are encouraging, promoting the people in India to go ahead with this fabrication and this ICs in India itself.
Okay, sir, second part is कि suppose we are having complex design like LNA or some more complex architecture. So, from where we can do fabrication for research purpose? Are there some specific labs available inside India where we can fabricate our designing?
Here in India, we have very limited resources. We can talk about SCL Mohali.
Okay.
We talk about ST Electronics, and at some of the IITs also, some of the good common institutes, we have these facilities where you can go ahead with these tasks, as mentioned.
Okay, okay. Thank you, sir. Sir, next question is related with processor. One participant asked that what is the basic difference between mobile processor and other processors we are using in laptops and etc.
Size-wise, you can say that definitely. If you talk about the computational performance abilities, we as on today we have as good processors on your laptops as we have on our mobiles. But definitely the series, the types will vary. So different vendors are preparing, keeping in view the size of a, that size of a mobile. If you talk of the today's, I was discussing about the recent development. We have actually standard latest generation of microprocessors, the 10th generation. They have gone beyond 5 gigahertz. They've even touched 5.3 gigahertz. So if you talk of the mobile applications, definitely on mobile also we can achieve the same performance, but the numbers or the type of processor or the type of chips that vendors are preparing will be definitely different. But we can definitely, as on today, we all see that we can experience the same performance achievements in your mobiles as well as on your laptops. There should not be performance-wise any difference as far as the ability of these devices is concerned.
Okay, okay, sir. Next one is, sir, as a learner, as a beginner, when we are using any platform, there are a lot of types of PMOS and NMOS coming inside the library. Then how we are choosing our PMOS or NMOS while doing our designing? Is there any some resource available to select specific PMOS and NMOS in particular designing?
Definitely, if you talk of the NMOS, if you have to talk about the transistors, over the years, we all started with PMOS, and with every transistor starting from PMOS to NMOS to CMOS, we have to see there are two basic constraints. One is speed, other is your power. So if it is low power,
Okay.
definitely you have to choose from the library low power devices. If the performance is the criteria, then from the available you have to choose from the high speed or high performance devices. So this way you can from different available voltages, your end requirements, what is your end requirement for your design? Is it low power or it is high performance? Accordingly, you can choose from the library different devices. और उसमें भी there are number of tools available. Vendors मैंने बताया back end पे है, front end पे आप किस पे काम कर रहे हो. Accordingly, there will be different tools, different libraries. So again, it's a very vast, intensive field. First, you have to decide कि आपको किस पे काम करना है. Back end पे काम करना है, front end पे काम करना है. And even if you talk of even one cycle, that is physical design cycle, it comprises of floor planning, partitioning, routing. So each of these steps is definitely a intensive work on its own. So you can choose one of these components because your final design, as I have illustrated this design flow, from your circuit design, logic design goes to circuit design goes to your final layout, and layout to then final device. So every design engineer at every stage is contributing, and design is being transferred to next. So the role of each and every design is different and is very important to have a final compact design of our requirement to meet our requirements.
Okay, thank you very much, sir, for a wonderful session. Now I would like to call our FDP convener, Professor Dr. Seema Naik, for vote of thanks.
Sir, it's a very informative session on IC fabrication, and he explained all the steps in details. Very good session, and I requested Dr. Rajiv to come for our session and share your knowledge. And thank you very much. He accepted my request, and thank you very much for the nice and informative session. Thank you, sir.
I think in the given span of time, I was able to do justice to the topics, because each of these contents, if you take at any section, processors le lijiye, even one processor, 86, 286, VLSI design flow, in itself is a very intensive and a large field, but hopefully in the given span of time, I was able to touch every topic, and I made my presentation in a possible way so that I was able to explain to the viewers. And lastly, I'd like to express my thanks to Professor Dr. Seema Naik giving this opportunity to interact, because as a teacher, I believe that we teachers are learners, and this is with these platforms, with these exposures, definitely we are able to share our knowledge, and we also grow day by day. Thank you very much. Thanks a lot.
Thank you.
Thank you, sir. Thank you, sir.